Now let's find the exact values of inverse circular functions. So for example, number 1, evaluate tangent of the inverse sine of negative 2/3 geometrically to find the exact value, and check your answer numerically. Okay? Now to find the value of our tangent of the inverse of sine of negative 2/3, first we have to find, or let's say, let y is equal to sine negative 1 of negative 2/3. Okay, so that's the inverse function. So meaning that sine y will be equal to negative 2/3. Okay, so that our version for the sine, if we have a uv coordinate axis, let's say, then let's graph first the location of negative 2/3. So following the SOHCAHTOA model, the SOHCAHTOA model states that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is O over A, and if we have a UV axis, normally UV axis is taken for the trigonometric functions to consider the location of the values in the trigonometric functions. So where is negative 2/3 here? Negative 2/3 means that the sine y is negative, meaning it's below. It's on the fourth quadrant. Okay? It could be on the third quadrant also, but we'd rather prefer it to be on the fourth quadrant. So let's use here, this is, let's say, an unknown number, and this is negative 2. Therefore, we could actually connect here for the tail going to the head. So this is our triangle. So this is our triangle, and this is negative 2. This is 3 being the hypotenuse, and what is this? This is, let's say, u. Okay, so following the Pythagorean property for right triangles, we have u square. This, let's say, this is our point uv. So that means we have u square plus v square is equal to r square. And in here, we could find u square as r square minus v square. So what is our u then? It would be positive or negative r square, and r is 3 here, so 3 square minus v square, that's negative 2 square. So u will be equal to positive or negative square root of 3 square minus 2 square, or negative 2 square. That would be square root of 5. And what will we use here? We have to use a positive square root of 5, because our u here is positive. Okay? So this is our u. Okay. Now our sine y here, because you're using sine y here, is negative 2/3. So what is tangent? This is our y. So if this is our y, we are actually finding tangent of y. Okay, so what is tangent of y? Now, based on our computation, our tangent of y should be opposite over adjacent. And opposite over adjacent means that we have opposite here as negative 2, and our adjacent as u, which is square root of 5. So our tangent y then would be negative 2 square root of 5 over 5. Okay, this is the answer. So to compute for it, to confirm it numerically, we have to use a calculator. Okay? That means that computing it numerically would give an impression whether our answer is wrong or correct. So we have first to get the arc sine of negative 2/3. That would be 2 negative divided by 3. That's equal to negative 0.667. And then get the inverse or the sine. That would be negative 0.7297. Numerically, this is negative 0.7297 approximately. Now if it's exact, then we will put an ellipse there. Okay, now let's find negative 2. So 2 negative times 5 square root equals negative 4 divided by 5. So how come? So we have negative 0.8944 here. Negative 0.8944. Okay, and in here we have negative 0.7297. So let's see tangent of negative 0.7297 negative, and get the tangent of this. That would be 0.8944. So we have the same answer. Okay. So let's move on to the other example. Evaluate y is equal to sine of cosine negative 1x geometrically to find the answer in radical form. Set your answer to y and plot it together with the original equation on the axis screen to confirm that your answer is correct. Okay, so let's start with writing the original equation. That's y is equal to sine of cosine negative 1 of x, or arc cosine of x. Okay, now let us use variables here. Let u, or let v, let's say, or let's say another variable. Let z is equal to cosine negative 1 of x, or arc cosine of x, then cosine of z is equal to x. So following SOHCAHTOA, that would be x over 1. And cosine of z is equal to x over 1. So the radius would be 1. This is x, this is y, and radius is 1. So from here to here would be 1. Okay? So let's call this as x. This is, of course, the u-axis, and this is the v-axis. So if this is x, this would be 1. And this is unknown. Let's call it a random variable. So this will be square root of 1 minus x squared, right? Because we have u squared plus v squared is equal to r squared, and our r is 1. So x squared plus v squared is equal to 1. V is positive, negative, square root of 1 minus x squared. And we will choose the negative part because it's below the positive y-axis. So we have negative square root of 1 minus x squared. Okay? But we could also choose the negative portion. So we don't have any restriction here, so we could have positive or negative square root of 1 minus x squared. So in this case, this y is equal to sine of the inverse of cosine of x would also be equal to y is equal to sine z. So if our cosine z is x, then if our cosine z is x and our sine z is equal to what we call sine z is equal to SOHCAHTOA, so it's opposite over hypotenuse. In this case, it could be, now let's just, for convenience, let's get the positive component. So it's equal to square root of 1 minus x squared all over 1. Or in other words, that's also equal to square root of 1 minus x squared. Okay, if there's no restriction given, then we could also have sine z is negative square root of 1 minus x squared. But for convenience, let's get the positive part of our elements. Okay, so this is example number 2. Example number 3, evaluate y is equal to the inverse or the cosine of the inverse cosine of x. Explain why the answer is reasonable. Set your answer equal to y and plot it together with the original function on the same screen to verify that the answer is correct. Okay, let's start with a given. The given is y is equal to cosine of cosine negative 1 or inverse cosine of x. This means that we have let z is equal to cosine negative 1 of x. So cosine z is equal to x. So in this case, we are also finding y is equal to cosine of z. So it's surprising that y is equal to z is also cosine z is equal to x. So therefore, the value of this given function is y is equal to x. Okay? Using transitivity and substitution. So this is the answer, without actually computing for it, which gives rise to a property of the inverse functions. And y is equal to x is actually a linear function passing through the origin, and this is a linear function. Okay? And since for cosine, our domain is, for inverse cosine, our domain is from negative 1 to 1, so we just highlighted from negative 1 to 1. Okay? Let's go to the property giving rise to a property which is called the composite of a function and its inverse function. So the function of the inverse function of x is equal to x, and the inverse function of the function of x is equal to x. These are composite functions, provided x is in the range of the outside function and in the domain of the inside function. Okay? So we're done with the lecture. Let us compute for problems 7 and 9. Okay? For problem set 7-6 in the next video. So for today we end up here. We end in the properties, and we're going to do some problems in the next video. So thank you for watching again.